So, hi guys, I hope you are doing extremely well. So, let's continue with the chapter of differentiation. So, now let's take a look at this, horrific chapter or one of the most scariest chapters of the entire syllabus of Further Maths IGCSE Edexcel. So, let's take a look at this. So, consider a scenario, okay? Consider a scenario where you've been given a car and your car is just traveling whoosh. All right. So a car has been traveling and starts from rest with an initial velocity of 0 and travels for 2 seconds and ends up with a final velocity of 30. Okay. So, well, your car now travels and you've been asked, what is the change in velocity? What is the change in velocity? Well, change in velocity is always denoted by delta V, which means the final minus initial velocity or 30 minus 0, which is equals to 30 meters per second. Well, no harm done. Well, what if you're asked to calculate what is the rate of change of velocity? Rate of change of velocity means delta v upon delta t. Change in velocity change divided by change in time. Well, your change in velocity is same as 30 and your change in time is 2 minus 0, which is 2, simple. And that comes out to be 15 meters per second square, or basically the acceleration. Well, there's a little bit of a trick to it, or a little bit of a catch to it. Whenever we say rate of change, it also means a derivative. Well, what is a derivative? Derivative is always change of A with respect to B. So, if I were to say change of A divided by change with B, it's always called a derivative or derivative. All right. So whenever two changes are getting divided, we say that we are basically calculating a derivative. All right. So no harm done. So I can also say, or if I were to, just copy this, yeah. So I can also say that delta v upon delta t is basically a derivative. All right. It's a derivative. It's a rate of change. It's a change upon a certain change. Change of A divided by change of B, and that is my derivative. And the standard denotation for that is that we can say change, we can represent change with delta, and we can also represent the change through another symbol, which is d. So I can write this entire expression of delta v upon delta t as well as dv upon dt. All right, so no harm done. dv upon dt can also be denoted to show the derivative or the change upon another change. All right, so no harm done. Well, now let's take a look at this example. We are pouring a liquid, from time 0 seconds, and the initial level of the liquid is 10 centimeter cube with an initial area of 5 centimeter cube. So now when we pour the liquid up to 5 seconds, we can see that our level rises to 40 centimeter cube. Okay, so our level rises to 40 centimeter cube and our area rises to 30 centimeter cube. So now if we were asked to calculate what is the rate of change, well, rate of change always means or rate of change of volume, right? So rate of change always means whenever we encounter the word rate, or let me just highlight it. Yes, the word rate always means dividing by time, dividing by change in time, dividing by delta t. Okay, it always means divided by delta t. And if we and because we are asked from the volume aspect of it, it basically means delta v upon delta t or dv upon dt. All right. So what's our change in volume? Our initial volume was 10 and our final volume was 30. And delta v means final volume minus initial volume divided by final time minus initial time, or if I could say tf minus ti. Just to show you, f means final and I means initial. So our final volume was 40 and our initial volume was 10, divided by our final time was 5 seconds and our initial was 0. So it comes out to be 30 upon 5, which comes out to be 6. All right. So 6 is basically our derivative. All right. It's our basically derivative. Yes. So it's a derivative, but there's a link to it. It's a rate of change. We can also call this the rate of change because our denominator included delta t. It included the change in time. So when we are all when so when are we so when we deal with a change in time aspect, whenever we deal with a change in time, it always means the rate of change, because the word rate by definition means dividing by delta t, dividing by the change in time. And in our previous example, it also meant the same. Because our denominator had a delta t, we could also say that rate of change of velocity, that is also called acceleration. So we calculate the rate of change of velocity, which means the derivative of velocity, and which means acceleration. So derivative of velocity, which meant acceleration, and derivative of volume. So we calculate the derivative of volume. All right. So if we encounter a situation where we are asked dv upon dA, well, let's calculate it. So our final volume was 40 and our initial volume was 10, and our final area was 30 and initial area was 5. So 30 upon 25. All right. And we can just simplify it further. It comes out to be 6 upon 5. So 6 upon 5, or in other words 1.2, is basically our derivative. And now it's not the rate of change. We cannot call this the rate of change because it does not include delta t. It does not include the change in time. So we cannot call this as rate of change. But what we can say is that it is basically the change of volume with respect to the change in area, and we can say that this is also a derivative. This is also an example of the derivative. All right. So this is also a derivative. All right. Derivative. Okay. So now let's take an example and inculcate our concepts for the graph aspect of our syllabus. When we are dealing with a straight line, well, what do we know of the straight line? We always know that a straight line has a constant gradient, right? So our gradient is constant. No harm done. And how do we calculate the gradient? Well, gradient is always change of y upon change in x, right? So no harm done and nothing new. So because we are dealing with two changes at a time, it means that this is also a derivative. All right? It's also a derivative. And now we can also say that, or we can use the standard notation of derivative, which is dy upon dx. Dy upon dx. All right? So no harm done. So when we calculate our gradient, which is constant in this case, constant here because of the straight line, we can say that it is basically dy upon dx, which is also constant because derivative is the gradient. So our derivative is always the gradient. So if I were to just draw a simple graph or simple subset or simple, Venn diagrams for you, or part of a Venn diagram. Okay. So our gradient and derivatives are linked in some cases. Our gradient is always the derivative. Gradient is always the derivative, but our derivative is not always the gradient. Okay. So gradient is basically the subset of the derivative. Now, when we are dealing with a curve, well, a curve has special properties. Our gradient is not constant. All right. It's not constant. So that poses a lot of problems. How can we calculate gradient at a certain point? For example, in this case, a point P. Or let me use just black red one for that. Yeah. So how can we calculate our gradient at point P? Well, that's quite easy. Well, how is it quite easy? We could simply calculate the derivative because we don't know. We absolutely don't know what the you know how could we just simply calculate it because we have no other clue. But we can simply calculate the derivative. And how can we calculate the derivative? Well, it's also really easy. We could just simply calculate the gradient of the tangent. So gradient of the tangent at that point, because we know that in a curve to calculate gradient at a point, we draw a tangent. You know, you have already studied this in your general maths. So we always draw a tangent at that specific point, and then we can calculate the gradient of that point or the derivative of that point, and that will be our gradient, and that will be our final gradient at that specific point. So derivative is basically gradient of tangent, and that's it. All right.